Welcome to Visual Algebra Lecture 5.9, Equivariance and G-set homomorphisms. Previously, we've seen that a G-set isomorphism is a bijection that commutes with the action. In this lecture, we'll start with the concept of a G-set automorphism. These form a group, and they can be thought of as symmetries of the action graph. If H is the stabilizer of any element, then the G-set automorphism group is the quotient of the normalizer of H by H itself. We'll see some beautiful examples of how we can identify this group both in the subgroup lattice and in the action graph. Then we'll look at the concept of a G-set homomorphism. Finally, we'll interpret the orbit stabilizer theorem as the fundamental homomorphism theorem for G-sets, namely that every transitive G-set is the quotient of G by the cosets of some subgroup. This is the fourth and final video in the mini-series on the structure of G-sets within this chapter, so don't miss this one. And it's starting right now. Let's recall the subtle difference between the concepts of action equivalence and the stronger condition of G-set isomorphism. And here's my favorite example that illustrates this from an earlier lecture. So D4 acts on the two sets of binary squares shown here. And these action graphs have the same structure, but the edges correspond to different elements. So over here, the blue edge is this horizontal reflection that is across the vertical axis, and over here, it's this diagonal reflection. So we need a different switchboard for these actions. So these are equivalent because there's this bijection, sigma, between these two sets, and also an automorphism from D4 to D4. That is like relabeling the buttons on the group, but that's not the identity. That is an outer automorphism sending F to RF. So these are equivalent, but for them to be G-set isomorphisms, we need to use the same switchboard. This has to be the identity. So here are the abstract notions of these action graphs if we fix the same switchboard. So here, H is the stabilizer of this element, and K is the stabilizer of this element. And remember, every transitive action we can represent as cosets of the stabilizer. And these things definitely are non-isomorphic as G-sets, even though the actions are equivalent. Throughout this lecture, we will only be comparing actions that are by the same group G and also use the same switchboard. That is, they're related by the identity isomorphism. So formally, suppose G acts on S1 and S2 via homomorphisms phi1 and phi2. Then a G equivariant map, or sometimes called a G map, is a function sigma between the sets such that sigma of phi1 of G equals phi2 of G of sigma for all G. And here's what that means. That means that this diagram commutes. So if we start with S1 and we press the G button and then apply sigma, that's the same thing as first applying sigma and pressing the G button down there. So here's what that means in terms of elements. Loosely speaking, equivariance means a map, sigma, that commutes with the action. Even though this is phi1 and this is phi2, they're different homomorphisms, we can think of them as, or I like to think of them as the same thing because we're using the same group switchboard. So press the G button, apply sigma is the same thing as applying sigma and pressing the G button. Here are four key concepts. The first two of these are old, and the last two are new, and it's worth comparing and contrasting them. Action equivalence involves an isomorphism between two groups and a bijection between the sets. G-set isomorphisms arrive when that isomorphism is the identity map and sigma is bijective. Sometimes these are called equivariant bijections, especially within combinatorics. G-set automorphisms also occur when the isomorphism is the identity and sigma is bijective, but now these two sets are the same. So S1 equals S2, which we'll often refer to just as S. And these form a group that we denote Hg of S. And finally, G-set homomorphisms also arise when we have the identity isomorphism. Anytime you see morphism and G-set, you can assume that's the identity map. But this time, sigma does not need to be bijective. These are sometimes called equivariant maps as opposed to equivariant bijections. So maybe G is acting on two sets and S1 is bigger than S2. So maybe this is an action graph with 6 nodes and this is an action graph with 3 nodes. And this is some structure preserving map from the bigger action graph to the smaller one, like a quotient. Let's start with an example to illustrate the concept of a G-set automorphism. And we'll take a familiar one, G being D6 and H being the subgroup generated by F. And here's that action graph. The big idea here is that a G-set automorphism can be thought of as a symmetry of the action graph. So when you look at this, I say, what are the symmetries of this? You should say, well, there's the identity, and then there's the 180 rotation. And that's it. So the 180 rotation, I'll call it sigma, that is a G-set automorphism because it commutes with the action. If we start here and we press the R button to go up here, and then we rotate this whole thing by 180, that's the same thing as first rotating it by 180 and then pressing the R button. Let me point out several important things with this example. First of all, this action, or just pressing the R button, right multiplies every coset by R. And this bijection, sigma, the 180 rotation, it right multiplies every coset by R cubed. However, because R cubed is in the normalizer are these two cosets, right multiplying by R cubed, so H R to the I times R cubed, is equal to left multiplying by it. So R cubed H R to the I. Because R cubed H equals H R cubed. So what that means is these two operations clearly commute. And I say clearly, why is that? Well, if we have H R to the I, and we multiply by R on the right, and then we multiply by R cubed on the left, it doesn't matter what order we do those in. They're independent from each other. And more generally, when we have an action graph like this, if we color the cosets that are in the normalizer blue, so here we have 2 of them, what I claim is that each blue coset is going to define a unique equivariant bijection or G-set automorphism like this. So here we have 2 cosets, and now what is this group that's blue? Well, what I am describing is the normalizer of H mod H. This is going to be the G-set automorphism group. Let's continue with D6 and look at several other subgroups that I think nicely illustrate this concept in tandem. So we'll take N to be the center, the order 2 normal subgroup. H will be the subgroup that we looked at previously of order 2. That's moderately unnormal because its normalizer has order 4. And then K will be that normalizer. That is fully unnormal because it is its own normalizer. So starting with N, if we take the quotient by it, then we get the group D3. You can see that right in the lattice right here. You can see that in the Cayley graph or the action graph right here. So let's take N and notice how this node is indistinguishable from locally from all of the other nodes. So there is a map that sends this to any other node. So the G-set automorphism group of this is D3. And I want to emphasize, this is not the well, in this case, it actually is the isomorphism group of D3. But in general, when we're talking about G-set isomorphisms, that's different than the isomorphism of the actual group. Over here, we have this action graph. H locally looks like only one other node here. So in the Cayley graph, the normalizer, mod H, has order 2. And so the G-set automorphism group here is going to have order 2 as well. Notice how these two nodes locally look the same and these two nodes locally look the same. Finally, K is its own normalizer, so the normalizer mod K is just trivial, and notice how K doesn't look like any other node in here. All three of these nodes look fundamentally different. Sometimes this is called a primitive G-set because it has a trivial G-set automorphism group. Here's my favorite example of G-set automorphisms and how they represent symmetries of an action graph. For this, I'm going to show you two groups of order 24. This is D3 cross C4, and this is S4. And I've highlighted two groups of order 2. Over here we have subgroup generated by H, and that's non-normal, so it's going to be one of these non-normal subgroups of order 2. Doesn't matter which one. Let's say it's this one here. So it's in a conjugacy class of size 3. And so that means that its normalizer has to have index 3. So that's up here. And we can see that this quotient has order 4. And we recognize this group, the subgroup lattice, as C4. So let me write that down. The normalizer of H mod H is isomorphic to C4. In contrast, over here, here's an element of order 2. Now this path, you do it twice, you get back to the identity. And you can check that this corresponds to one of the pairs of transpositions in the symmetric group. So it might be something like 1, 2, 3, 4. So this is going to be in a size 3 conjugacy class as well. So the normalizer of this also has index 3. So it's got to be one of these things up here. If it's this one, then it's got to be that one up here. And we can see that the quotient of this normalizer by H is V4. We recognize this subgroup lattice. So here we have the normalizer of H mod H is isomorphic to V4. So I claim that when we collapse by these subgroups, we will get an action graph that over here will have C4 symmetry and over here will have V4 symmetry. So let's see those action graphs. And here they are. One day I actually took these two order 2 subgroups and I found the right cosets of them. I think I color coded them on this Cayley graph, and then I collapsed by them and figured out how to rearrange them nicely to get action graphs. Do you see the cyclic C4 symmetry in here as guaranteed by the quotient of the normalizer by H being C4? Do you see the V4, the Klein symmetry, over here as guaranteed by the quotient of this normalizer by H being V4? Isn't that neat? Again, this is my favorite example to illustrate this concept. Now that we understand what the G-set automorphism group really is, let's prove that statement that we claimed earlier. That is, for any subgroup H of G, if we take the set S of the right cosets of H, in other words, we collapse or quotient by H, then the resulting G-set automorphism group is just the quotient of the normalizer of H mod H. And just for reference, here are those 3 examples of G-sets from D6 that we saw earlier. And here's how the proof will go. We'll take an arbitrary unknown G-set automorphism sigma, and we'll prove a lemma that sigma applied to any right coset Hg has ascended to Hxg for some fixed element x in the group. So it has to stick in this x between the subgroup and the coset representative. We're to call such a map sigma. Next, we'll prove that this map up here is actually a G-set automorphism if and only if x is in the normalizer. And when that happens, well, that means that xh equals hx. So this map that I've defined above is really left multiplying a right coset by x. And notice how left multiplying by x commutes with right multiplying by g or by anything else. And finally, we will show that two of these maps, sigma x and sigma x prime, are the same if and only if x and x prime, the corresponding elements, are in the same coset of H. Now, we don't quite phrase it like this, but it's equivalent. So up through lemma 2, what we've done is we've shown that every element in the normalizer of H gives rise to a G-set automorphism. In other words, we have a map F from the normalizer of H to the G-set automorphism group of S, and it takes an element X and sends it to sigma of X. We will show that the kernel of F is equal to H. In other words, two things are the same if and only if their elements are in the same coset of H. And then our theorem will follow immediately by the fundamental homomorphism theorem. Isn't that neat? Let's prove that first lemma. Formally, any G-set automorphism sigma, where sigma is the set of right cosets of H, is determined by the image of H. In particular, if sigma sends H to Hx, then sigma sends a right coset Hg to Hxg. And let's prove that. So since sigma is G equivariant, or in other words, since it's G-set automorphism, it commutes with the action. In other words, the following diagram has to commute. So if we start with S and we press the G button and then we apply sigma, that has to be the same as first applying sigma and then pressing the G button. So for this to commute, let's start with H and let's send it. So we press the G button. We have to get Hg. And what we're trying to figure out is, this is what we're trying to show. So we want to see where this gets mapped. This is sigma. So when we apply sigma, suppose that sigma gets sent to Hx, and then we press the G button, we know this has to get sent to Hxg. Again, that's the definition of phi of g. So sigma, in order to make this diagram commute, has to send Hg to Hxg. Now, I'm not saying that every x will define, and this is going to be a well-defined map for every x, but if this is a G-set automorphism, then it has to send this right coset Hg to Hxg. Okay, now that we know that every G-set automorphism has to be of this form, instead of calling it sigma, we can call it sigma x. And what we claim is that the only such map that is going to work is for x being in the normalizer. So let's prove that. We'll do the forward direction first. So let's assume that this sigma x is a G-set automorphism. We'll show that x is in the normalizer. So let's say that sigma x is indeed a G-set automorphism of the right cosets of H. And let's take some element little h in the subgroup H. Now, because this is a G-set isomorphism, it commutes with the action. So let's compare. Well, if we press the little h button and then we apply sigma, that better be the same as applying sigma and then phi of h. In other words, pressing the little h button. So in terms of elements, well, we can start with any left coset. Let's start with h. And let's press the little phi of little h button. And if we do that, we multiply this by an element in H, so we just get H itself. That's our boring but useful coset lemma. And then when we apply sigma x, we get Hx. And then when we apply phi of h again, we're just multiplying by little h. So we get Hx little h. And now this here, Hx little h, has to be the same as going this direction, first multiplying by h, which does nothing, and then multiplying by x. So so this has to be the same as Hx. So that's what happens when you apply sigma h. And so these things have to be the same. Hx little h equals Hx. So what does that mean? So those are the same. I.e., for all elements little h in the subgroup, we must have Hx. Well, let's first just move the h over here, or the x over here. So let's write this as Hx little h x inverse equals h. And that's the same thing. It's equivalent to saying that this representative right here, x inverse, is in H. And that's exactly what it means for x to normalize H. We take something in H, we conjugate it by x, and we get within H. So that means that x is in the normalizer. And that's exactly what we wanted to show for, again, for this forward direction. Now let's prove the converse. So we're going to prove the reverse direction. That is, we will assume that x is in the normalizer. So let's say that x is in the normalizer. And let's pick some coset Hg in the set S of right cosets. So by lemma 1, we know that the map sigma x sends Hg to Hxg. So that's what we showed earlier. But we also know, since h is in the normalizer, we can write this as Xhg. And now we see that we have two operations. Right multiplying by either g, or we can multiply this coset by some other element. Right multiplying, which is the action, clearly commutes with left multiplying by x, because it doesn't matter what order we do those in. And that's what it means for this to be equivariant. In other words, to be a G-set automorphism. That's really the only missing piece. So let me just say that phi of, or sigma x and phi g commute. Maybe I should use a different element than I picked a coset here, but it's fine. I can use this g. Use commute, and let's just see why that is. So what we need to show that. So what we're trying to show is that this is a G-set automorphism. In other words, that this map is equivariant, and so we have to show that this commutes. I said pick this element. Maybe what I should have done is I should have just said, or pick G and G. That's really all that we needed. And now let's take a coset in here. I'm going to take HA just because it's different. And let's press the G button, right multiply by that. So we get HAG. And then let's apply sigma x. So we left multiply XHA. I mean, again, left multiplication, right multiplication commute. You can really see this. Sigma x is XHAG. So multiplying this by phi, or by g, this thing here is really Hxa. So again, the h moves left. So if we right multiply by g, left multiply by x, that's the same thing as left multiplying by x and right multiplying by g. And so, you can move this x over here if you want. And that's exactly all we needed to show for this to be equivariant, or in other words, a G-set automorphism. And that's the end of the proof. Now that we've proved the two lemmas, we are ready to prove the full theorem. So again, if G acts on the set of right cosets of a subgroup, then the G-set automorphism group is the quotient of the normalizer by H. To prove this, let's define the map F from the normalizer of H to the G-set automorphism group of S that just sends an element X to this map sigma X that we defined, which is left multiplication. So remember, sigma X takes a right coset and sends it to Xhg, which is Hxg. And we can do this because it's in the normalizer. Let's now check that this is a homomorphism. So we need f of xy to be equal to f of x, f of y, or equivalently, sigma xy equals sigma x times sigma y. So sigma xy, if we take x, or take Hg, sigma xy sends it to Hxyg. Whereas if we take Hg, and now we first apply sigma x, remember we are reading from left to right, we get Hxg, and now we apply sigma y, we get Hy. Ooh, look at this. So it's actually, you know what? This is a left action, because we're left multiplying. We can move it over because of the normalizer, but we have that left versus right action issue. So actually, technically, I think I'm going to have to define f to send x to sigma inverse like this. And now that's going to send this and this, and then this is going to hold. So go back and watch that action equivalence lecture for the details on this. But yeah, this will work if we define it like this. I'm going to pretend that we don't have to do this because it's not really going to matter. Well, it's fine either way. I'll stick with it. So why is this onto? It's onto by Lemma 2. So by Lemma 2, every G-set automorphism had this form. And then what about the kernel? So the kernel of f equals h. This is what we have to show. So let's do both containments. So let's take an element in the kernel of f. That is the same thing as saying Hg equals Hxg. And now I should really put inverse right there based on this little detail that I had to fix. Again, this is not why it's not going to make a difference. This is if and only, we just right multiply by g here. And this is the same thing as saying h equals hx inverse. And that's the same thing as saying x is in h by our boring but useful coset lemma. And again, it really doesn't matter whether we say x is in h or x inverse is in h. H is a group. And finally, let's do the other containment. So if h is, so let's take something in h and show that that the corresponding map up here is in the kernel. This is going to be straightforward. If h is in h is in big H, then sigma left multiplying by h is going to send the coset h little g to h, now I have to say h inverse little g, which is equal to hx, because by our boring but useful coset lemma, that's just equal to h. So again, this is why I said it doesn't really matter. It does matter, but for these details, x or x inverse, everything still holds. So now the result follows from the fundamental homomorphism theorem. So let's apply the fundamental homomorphism theorem, and we get that this is a homomorphism with kernel H, and this result follows immediately. And that's the end of the proof. I want to take a few moments to cast what we've seen in the setting of subgroup lattices. So we've let G act on the set S of right cosets of G via some action, via some homomorphism. And I like to say quotient G by H, or collapse, even if H is not normal, and we still get a G set. So if H is not normal, then what we have is we have a conjugacy class of size bigger than 1, and the normalizer is the largest subgroup in which H is normal. That's just by definition. And remember, the kernel, that's the intersection of, or it's the base of the conjugacy fan, the intersection of the conjugate subgroups. We did that earlier this chapter. This is the largest normal subgroup contained in H. That's something that we also proved, that the intersection of conjugate subgroups is the largest normal subgroup contained in it. So there's kind of a duality here. The largest subgroup in which H is normal is this, and the largest normal subgroup contained in H is the kernel. This quotient represents the symmetries of the action graph. That's one of the big ideas here. And then this quotient, so H is like the non-trivial things that stabilize this, and N are the broken buttons. So the quotient H mod N are really like the group of non-trivial things that stabilize H, and not, so we're ignoring the buttons that are broken. So compare this to when H is normal. So when H is normal, then our conjugacy class has size 1. So the kernel is equal to H, the largest normal subgroup contained in H, in this case, is equal to H. And then the largest subgroup in which H is normal is equal to G. And then the G set automorphism group is this quotient G mod H. Again, that's not necessarily the automorphism group of G, but it's just saying that this node H or N, it looks like every other node. So there is a map that sends this to any other node. So I don't know if this helps or not, but I think it's nice to sort of compare and contrast when H is normal and when it's not, and the difference between the normalizer and the kernel, and in particular what these two quotients mean. I want to finish with the concept of a G-set homomorphism, because these are objects that we've been looking at all chapter, and it's important to understand structure-preserving maps between them that are not bijective. So if we drop bijectivity of the map sigma, then we get a G-set homomorphism, or sometimes it's called a G-equivariant map. Here's an example that I think you're really going to like, using D6. So we've seen this before. This has two symmetries, and the normalizer is in blue, and then the cosets of the normalizer are in various shades of red. And notice how these two nodes or cosets are locally identical, as are these two and these two. So if we collapse by those, there is a structure preserving map from these 6 cosets to these 3 cosets. You can see how this goes. You just take a coset and you map it to the larger coset of the normalizer that contains it. This is a G-set homomorphism. It can be described by the following commutative diagram. Again, we take a coset, right coset of H, and we send it to the corresponding right coset of K. And notice that if we multiply by G, and then we apply this map sigma, which you can think of as left multiplying by X, that's the same thing as first doing that and then right multiplying by G. So I'm not going to go over the details, but hopefully, we're used to thinking of quotients as collapsing Cayley graphs. It should be pleasing to see that you can do the same thing here with action graphs. So we say that the map sigma commutes with the action of the group, even though these sets are different and different sizes. And here's that example one more time in terms of a commutative diagram. So if we start with H and we press the R button, we go up here, and then we send it to the corresponding coset via sigma, coset of K. That's the same thing as first sending this to the corresponding coset of K and then pressing the R button over there. Finally, I want to say one last comment about the orbit stabilizer theorem. I could have said this in an earlier lecture, but I didn't feel right doing it until we defined G-set homomorphisms. And I claim that the orbit stabilizer theorem, what it's really saying is it's the fundamental homomorphism theorem for G-sets. So the orbit stabilizer theorem, is this bijection between the orbit of S with the cosets of the stabilizer. But not only is there a bijection here, but I claim that these things are isomorphic as G-sets. So the quotient of G by the stabilizer is isomorphic to the orbit. So here's D4. It's kind of matching the diagram that we did when we learned about the fundamental homomorphism theorem last chapter. And consider a transitive action that we've seen on these 4 binary squares. I claim that this here is the orbit of S, and that is isomorphic to, you can first collapse by H, take the quotient by H, and then apply this G-set isomorphism from, so this is H mod G to the orbit. So I've been using right orbits throughout, so it doesn't look as good to say the stabilizer of S mod G is isomorphic to the orbit of S. It looks, if you use left actions, you write G mod the stabilizer of S is isomorphic to the orbit of S. And I've ragged on the notation that I really don't like, but what some people do is some people write the stabilizer of S as G sub S, and then they write the orbit of S, these are left actions now, as G dot S or just GS. And so if you do that, then you get this really nice looking theorem. It's just a couple of symbols, which is the orbit stabilizer theorem. Even though this is nice, again, I like saying things that are more descriptive like this. But in plain English, whether you use right actions or left actions, the orbit stabilizer theorem you can say is that G mod the stabilizer is isomorphic to the orbit as a G set. And that is a generalization of the fundamental homomorphism theorem, which says G mod the kernel, or G mod, if you collapse by a normal subgroup, the resulting quotient is isomorphic to the image. So I think that's a neat little perspective, and I hope you enjoyed that. And that's the end of our 4-part mini-series on the structure of G-sets. We have a couple more lectures left in this chapter, and those will be on the CELO theorem. So That is all about how to classify groups of order p to the n times m. So if you want to understand groups of order 72, you should understand groups of order 8 and of order 9 and the subgroups of those orders and how to put those together. And even though that sounds like the structure of groups and not really any topic involving group actions, the proofs of the C₄ theorems really involve clever use of group actions. So I think you're really going to enjoy that. I hope you stick around, and I'll see you then.